Now I would like to introduce our speaker, Chengyuan Zhang. Today, he will share his research about Bayesian calibration of the intelligent driver model. Chengyuan Zhang is a PhD student in the Department of Civil Engineering at McGill University. He is also a visiting researcher at Robotics Institute at Carnegie Mellon University. His research interests are Bayesian learning, macro and micro driving behavior analysis, and multi-agent interaction modeling and intelligent transportation systems. To who wants to know more about him, there is a website link in our flyer, so go get him. So with all this said, now let's welcome him to start his presentation.
Okay, thank you. Thanks for Gary for the invitation and organization of this web seminar. So welcome to today's session. So this project is going to be a Bayesian calibration of the intelligent driver models. And this project is advised and supported by my advisor, Professor Li Junsun. So in today's talk, we are going to focusing on the car following models and how to calibrate it, how to do better simulations. So feel free to ask any question in the chat window, and I can see the chat window at any time. So so in today's talk, we are going to focusing on the car following model. So the motivation of the car following model is like, how would the following vehicle react in response to the leading vehicle? So what is car following? It is like one following vehicle is need to take any actions in response to the leading vehicle. And for example, here is a trajectory on the highway. And if we just select zoom in this specific area, and we just extract two trajectories here. One trajectory is the leading vehicle, which is in the right line, and another trajectory is the following vehicle. And what we want to do here is we need to consider a problem of how to simulate the motion of the following vehicle. For example, if we have already observed the leading vehicle, which is the right line, and we have, for example, we have a following vehicle at a specific situations, and how to simulate it, how to make dynamic decisions in the in response to the leading vehicle. This is what we want to do. And then we bring to another question is, what do we need for the simulation? And before we need to know what are actually needed in the simulation, we need to know the goals of the traffic simulation, right? Such that we can make our target and we can make the specific plans for the simulation. So the goals of the traffic simulation in the past was to reproduce traffic phenomenon. And from now on and in the future, we need to support the development and types of control algorithms. For example, we need to develop the CAVs, we need to develop reinforcement learning algorithm for traffic control or management. And we also need to investigate in the interactions between human drivers and the CAVs, or even more like social interactions between human drivers. And we need to improve the safety. We need to make it more predictable, and we need to reduce the uncertainty of the simulation or the algorithms of the CAV, right? So this requires us to make a simulator with human-like driving behaviors. So what's the character of the human-like driving behaviors? First, they have some physical inertia, right? They won't just make abrupt acceleration and braking within a short period. And humans do not drive according to accurate measurements. They don't drive according to some digits or some number, but they drive based on their feelings, right? So such a decision-making mechanisms introduce randomness. So when we are simulate, we need to take these factors into consideration. Therefore, the deterministic car following model cannot achieve all of these factors, right? So this requires us to develop a human driver car following model. So in this talk, we're gonna focusing on the first is how do we learn a human driver car following model? And the second is how do we simulate human-like car following behaviors? The outline of this talk will be first, let's review the intelligent driver models. And by the way, this whole framework is just a Bayesian calibration of the car following models. And we just use IDM as an example. And if you want to change like to other car following models, say like OVM or other things, it's also adaptable. Okay, so first we will briefly review the IDM, and then we will propose a probabilistic modeling framework. And there are three models in this framework: the Bayesian IDM, and the IDM combined a Gaussian process, and IDM combined the autoregressive process. Then we will demonstrate some numerical experiments for calibrations, and we will illustrate how we do simulation with respect to these models. And finally, we will get to the whole framework. So let's first look at a general view of the data generative processes of human driving behaviors. For example, first we have the human driving behaviors, and we have any different kind of sensors. We need to observe some data from the behaviors. And these sensors are actually noisy and not perfect, such that in the observation process, we have some ID noise here, such that we can obtain our observations. And our goal is to develop the car following models based on the observed data to approximate the human driver behavior. And in this talk, we're focusing on a very simple car following models, which is IDM. And the intelligent driver model is actually very simple. It models the following behaviors at each time step. And it mainly has three inputs. The first is the speed, and the second is the relative speed, and the third is the spacing between the following vehicle and the leading vehicle. And it only has one output at which is the following vehicle's action at the current time step. So although it looks like a very complicated equations, it only have 5 parameters here, control all the equation and 3 inputs. The inputs are just as I said before, and here are the 5 parameters that controlling the IDM. So when speaking of the IDM calibration, it means a task that once we observe our car following data, we want to identify these 5 parameters such that the model can make a decision as close as possible to the human driving actions, right? So this is what is calibration. And when we're doing the calibration, we have different kind of assumptions based on our model. Basically, IDM just assumes that the ground truth acceleration versus the action taken by the human drivers equals to the IDM deceleration plus an ID error term. And basically, we just calibrate this IDM by MLE, maximum likelihood, by using the normal distributions, or we just minimize the loss of functions, say like using root mean square arrows between the arrows of velocity or the location, or even some of them just combined acceleration arrows. So all of them are just based on this simple assumption, is that the real acceleration equals to the IDM plus the ID arrow. However, is this true? We need to think about this. This is a generative process again. And if we have a perfect human driver behaviors, it adds some ID noise, then we have the observed data. So if we assume the noise are still ID white noise, it means that we assume our model is a perfect car following model, right? So once we have a perfect car following model, we can assume that it is a white noise ID, right? But is IDM a perfect car following models? Let's have a look. Let's say this is a well-calibrated IDM, and the black lines here are just the human driver data. And the right line here is just a decision made by the IDM. And we can see that there are still something left between the gaps of the IDM and the human drivers. So if we measure the gaps between the IDM and the human driver data, we can obtain the residuals, which is shown in the lower figures. So the residuals is actually a continuous curve along time, but not IID white noise, which means that the IDM captures much information, but some information are still left in the residuals. So if we want to get a perfect model, we need to combine this information. We cannot just discard it and just left it in zero, right? So we need to combine this information while calibrating, such that we can calibrate an unbiased IDM model. So this makes us to reflect that for human driving car following model, what do we still miss? For example, we lack of the reaction time. We didn't have the reaction time in the IDM model, right? Because it's just a real-time response. And we didn't model the temporally correlated errors. We don't have the time delays because IDM as a parsimonious model can hardly explain all the variance in the data. So as a result, the residuals are just serially correlated. We don't have the model's anticipations of like what would be the next step of the human drivers. Do it want to just accelerate or decelerate, right? We don't model the heterogeneity of the drivers. So how do we investigate these factors when calibrating IDM? In this talk, we're going to focus on modeling the temporally correlated errors while we develop the heterogeneity of the drivers. Okay, so our solution is combining the IDM and the time series modeling techniques. So basically, IDM assumes that the ground truth data equals to the IDM plus an IID error. And here we just assume that we plus another temporally correlated residual errors other than IID and the IID error and the IDM term. So for example, we can use like many other time series modeling technique, for example, Gaussian processes. In the latter figure, these are just samples drawn from the Gaussian processes. And in the right part is just the residual trends that we have shown before. And as we can see here, some GP samples look very similar to the residual trends, right? So which inspired us to model the residuals using a Gaussian process. Here we just combine the IDM and the Gaussian processes, and such that the likelihood becomes like it is a normal distributions with the mean function as the IDM, and we have a temporal correlated term here and plus an IID term here in the covariance matrix. And here we just use the RBF kernel, and its form seems like Gaussian distributions. There are two key hyperparameters in this RBF kernel. So one is length scale, and this is L here. The length scale actually describes how smooth a function is. For example, small length scale value means that the function value can change quickly, and large values characterize functions that can change, only slowly. So length scale also determines how far we can reliably extrapolate from the training data. And we have another key hyperparameter here called sigma k. And this sigma k specifies the scale of the variance. So based on the idea of combining GP and IDM, we have a name for this model. It's called memory augmented IDM. So shorthand is MAIDM. So basically, again, MAIDM assumes that the acceleration data Gaussian process term plus ID error. And based on this assumption, we can develop a Bayesian hierarchical model. So here we have a pooled model, a hierarchical model, and unpooled model. I will not explain details on the differences among the pooled model, the unpooled model, and the hierarchical models. So here we just focusing on the hierarchical model because it can simultaneously model the driving behaviors at the population level and the individual level. Okay. So here is the specific detailed equation of the our model. So first we can sample a populational level behaviors theta here. And then we set this population level behavior theta as the prior of the individual level behavior theta d. And here is basically the hierarchical model, and in such a way we can simultaneously learn the population level behavior and the individual level behaviors. And the differences between the Bayesian IDM and memory augmented IDM is this term, the Gaussian process term. We combine the length scale and the variance term into the kernel matrix, and such that we can combine the Gaussian process into the whole calibration scheme. So experiments. We want to try to calibrate the IDM on some data. So here we just use the Hardy data set. And we select 20 leader follower pairs. And recall that IDM model is just a very complicated equations, and it contains 3 inputs and 1 output. And the key parameters are just the 5 parameters here, say like alpha, beta, V null, S null, and T. So we need to provide plenty of information to our IDM such that it can calibrate all of these 5 parameters. For example, if we want to calibrate well, the data should contain acceleration behaviors such that we can learn a good alpha, because alpha is meaning some like acceleration term. And we need to combine some deceleration data such that it can learn a good beta, because beta means that deceleration behavior. And like other parameters, say like we need to involve the free flow drivings, and in order to learn well S null and T, we need to involve some following behaviors with distance keeping. So which means that we need to provide plenty of information to our model. Therefore, we select 20 pairs of data. So as you can see here are just they contain some stop and go behaviors. And by the way, these data are all extracted from the Hardy dataset. And here are the calibrated results. So in the left part, it's just different kind of models. And in the middle part, it's just the 5 parameters of the IDM. And in the red part, we have the white noise level, which is a standard deviation of the white noise, which is ID noise that we assume. And we have the GP variance term and the GP length scale. So the upper part are just a Bayesian IDM, and we assume the ID noise for the Bayesian IDM, so it doesn't have the GP length scale part and GP variance term. So if you look at the white noise term, these are actually very large. And in the lower part, we have the Gaussian process term, the Gaussian process plus the IDM model. And as you can see here, the white noise term for the Gaussian process are actually at a very stable level, right? And the length scale is just also very stable. It's approximately 1.35 seconds. And this is actually very good. And for the Bayesian IDM, we have a bias estimation because we have a very large white noise. And for the MA IDM, we have unbiased estimation. And out of the white noise here is just approximately to a very small value. And another observation is that the total variance of the noise, say like the square of the sigmas epsilon plus the square of the k, is smaller than the square of the epsilon for the Gaussian for the Bayesian IDM. Okay. And also a very interesting finding here is that the length scale is approximately equal to 1.35. So which means that the decisions only have correlation with the data within 4 to 5 seconds. Because as I said before, the RBF kernel seems like a Gaussian distributions. And the length scale here is similar to the Gaussian distribution of the sigma, which is a variance term. So which means that the data sampled outside of the 3 sigma has just no correlation with the decision right now, right? So which means that we only have correlation with the data within 4 to 5 seconds. And here are the posterior distribution of the calibrated parameters. So we can see they have similar distribution shape for the Bayesian IDM and the MA IDM. So which also inspired us, like we can draw different samples or say different IDM parameters from these posterior distributions, which gave us the idea of doing the simulation. So in the simulation task, traditionally we have the deterministic simulation, right? Because we have just provide the leading vehicle's trajectories, and we just update the decision of the following vehicle based on IDM, and IDM is deterministic. It's just output one value at each time step. So here we propose a stochastic simulation method. So let's briefly review that our MA IDM assumes that the acceleration data equals to IDM term plus the Gaussian process term plus an ID arrow. So we need to simulate each term at each time step. So for example, for a specific time step t now, we need to obtain the first term A IDM. We just take the input here and we have the output. And second, we need to evaluate these randomly drawn functions at time step t. And third, we just draw a random ID noise plus to the term. And by the way, the second step and the third step can be combined by sampling from a conditional Gaussian distributions. And here are the stochastic simulation results. And instead of just given a single line of trajectories, we can actually have a distribution of the trajectories, which we call the posterior trajectories. And in this figure, the black line are just the ground truth or say the human driving data. And the MA IDM are illustrated in the red lines, and the Bayesian IDM are illustrated in the blue lines. In the upper part is the acceleration decision of the following vehicle. And in the middle part is a velocity, and in the below part is just a spacing between the following vehicle and the leading vehicle. So we first fix the trajectory of the leading vehicle and provided the initial motion state of the following vehicle and do the simulation multiple times. So we have briefly results here. So stochastic simulations can actually contain the ground truth curve in its envelope. For example, let's look at here. The red line can actually contain the black line. By the way, the black line is the ground truth, and which means that our estimation is unbiased. But for the IID estimation, which is a Bayesian IDM, the blue line actually have a deviation from the ground truth, right? So which means that this is a biased estimation. So briefly, MA IDM has a better calibration results than Bayesian IDM. even Bayesian IDM is reached a larger level of noise areas, it still cannot bridge the gap. So we have another, result to show the gap between the leading vehicle and the following vehicle. So in this figure, the upper part trajectory is a leader, and the lower part, the black dotted line are the following vehicle. And we just plot all of our simulation results on this figure, such that we can have different distribution of the simulation. So actually, the action uncertainty is scenario specific. For example, if we look at the variance of this simulation, we can see that, where is my pen? Okay, here. We can see that at this specific area, we actually has a very low variance, right? Because at this part, the leading vehicle is braking. So all drivers has to decelerate. But when the leading vehicle accelerates, say like in this area or this area, the actions are more uncertain at their own view. The driver can either take a big acceleration to follow up, or just keep the current speed and keep a larger distance from the lead vehicle. So another interesting result is still coincides with previous results. Is MA-IDM has a better calibration results than the Bayesian IDM. So currently we still have a very good results for the simulations, but we need to think about it again. When we're doing the simulations for the Gaussian process, we need to iterate step and step, which means that we need to do the conditional Gaussian distribution again and again. And as you know, that the Gaussian process is actually very computational expensive. So also MA-IDM has a good calibration result. A simulation can be very slow, which means that we need to think about one question. Is there a better way to do simulations? So let's go back to the initial idea that we had before. So what we want to do is that we want to combine the IDM with some other time series modeling techniques. For example, the IDM assumes that it is ID, and we just assume that it is IDM term plus a temporal residue term plus an ID noise, right? So here we just use the autoregressive process instead of Gaussian process to model the residue term. And the the autoregressive process is much simpler than the Gaussian process term because it is just a simply combination of the history step. So to make the correspondence, we can see that the blue term is the IDM, and here we just plus another term, which is a temporally correlated term, and the ID term would be just the blue part. And as you can see in the red part of figures, I just draw different kind of samples from autoregressive with order 5. And you can see that it is still looks much similar to the residue trends that we had before. So based on this assumption, we can develop a probabilistic graphical models at the left part figure. And we also have a name for this combination of IDM plus autoregressive, which is called dynamic IDM, because this is just the IDM based on Bayesian dynamic regression. So again, we just assume that we have another temporal correlated term, and we use autoregressive process to characterize this temporally residue term. And we have some simulation results to compare with the Gaussian process term plus the IDM. So in the left part is the MA-IDM, which is the Gaussian process plus IDM. And in the right part is just the dynamic IDM, which is AR plus IDM. So I think the comparison is very straightforward, and we have the brief result here. It's just the dynamic IDM can also obtain unbiased estimation, and it can also have lower variances than MA IDM. And we also have like the posterior trajectories here. As you can see, in the red scale, we have the variance term of the posterior distributions, and the dynamic IDM can have a much lower variances than the MA IDM, right? And in the meanwhile, the dynamic IDM can also contain the ground truth in its envelope. So let's evaluate the simulation. So we have some numerical evaluations here. We just use a short-term, say like 3-second simulation with different models. And in the simulation setting, we just randomly select, say like 50 points from the time step. And at each time step, we do the simulation as a previously, what we have done before. But this time we just do short-term simulation for like 3 seconds. And here are the results between the simulated trajectories and the ground truth trajectories. Say we select RMC based on acceleration, based on speed, based on spacing, and we also use CRPS, which is a statistical evaluation methods. We also based on acceleration, speed, and the spacing. And overall, we can know that the dynamic IDM is better than Gaussian process plus IDM, and which is much better than Bayesian IDM. So briefly, we can summarize like the reason that AR IDM is better than GP IDM is it can make simulation faster, and it can have better calibration result. And the GP IDM is better than Bayesian IDM is because it can provide unbiased parameter estimation. And furthermore, the Bayesian IDM is better than the traditional IDM is because it can provide the probabilistic estimation. It can give, the posterior distribution that the parameter that is calibrated, and it can also build a hierarchical model which can simultaneously estimate the populational level behavior and the individual level behaviors. So if you say that the dynamic IDM can make the simulation faster, which means that we have a solution for the long-term simulation, right? So how about the performance of long-term simulation? Here we use another data set to conduct this long-term simulation. So previously, we just simulate for like 60 seconds. And here we can simulate for 1,000 or 2,000 seconds in the simulation. And again, this result is very amazing because I only provide the leading vehicle and the initial state of the following vehicle. And I let the IDM simulate for like 1,000 time, for 1,000 seconds. And in the end, the IDM can still follow the ground truth trajectories here. So I feel like the result is very amazing here. And in the upper part is just the ground truth data in the trajectories. So these are the experimental setting is like 5 CAVs, one following each others. So this is actually a platoon. And here we just have selected one vehicles from them and just follow the leading vehicle. So as I said before, if this is a platoon data set, which means that we can simulate the platoon, right? So if we provide the very first leading vehicle and we use a calibrated IDM for the following vehicles, we can simultaneously simulate 4 following vehicles at the same time, right? So here I just select a region from the OpenACC dataset, and we provide the first leading vehicles, and we simulate the 4 following vehicles. And again, the black line here is just the ground truth data. And we just draw different posterior trajectories by using our calibrated IDM. As you can see here is that when we're simulating in the multi-vehicle scenarios, the IDM can still perform very well. And it can replicate the plateau trajectory of the ground truth data. So if this is not enough, we can furthermore simulate the multi-vehicle scenarios in a ring road simulation. So let me briefly illustrate what is a ring road simulations. Say we have a circle here, and we have different vehicles distributed equally on this ring road. And we just simultaneously simulate all of this in the same time, and such that we can, observe different traffic phenomena. And for the upper part, it's just we simulate using Bayesian IDM, and we just fix the IDM parameters as what we have already done in the traditional simulation, right? So as we can see, it can replicate some like shock waves, but it can just repeat the patterns again and again. And in the middle part is the simulation with GP plus IDM. And we can see that we can simulate some shockwave formation and dissipation, right? And in the lower part, we have the similar results with the MA IDM, which is simulating using the dynamic IDM. And we can also have some phenomena of like shockwave formation and dissipation. So, okay, to summarize, the whole framework is, first, we can generate diverse type of drivers because we developed a hierarchical model, and we use a Bayesian calibration method to provide the posterior distribution of the estimated trajectories, the estimated parameters. And then we can simulate draw different samples from the posterior distributions, and then we can simulate different kind of IDM drivers. And secondly is that we can produce a very good uncertainty for each driver because we combine the time series modeling techniques. And the third is that we can simulate human-like car following behaviors because we develop the stochastic simulations. And here are some interesting takeaways. The first is that we need to know the importance of the probabilistic simulation. And as I have shown before, maybe you can realize that the deterministic simulations are actually not enough for us to develop a human-like driver simulator. Okay, so and the second important takeaway is that we have a conclusion that the length scale is about 1.35 seconds. And recall that what length scale means. It means that we only have relation with the data within 4 to 5 seconds of our input data, right? So which means that when we are designing other car following models, 4 to 5 seconds of history data is a proper choice to select it as your input data. Okay, so third takeaway is that we need to provide enough information to calibrate a good car following model because I see some of the calibration approach are just select the random trajectories and say like we just use this trajectory to calibrate. But actually, IDM has 5 parameters, and you need to cover all of these parameters in your scenario, such that you can have a good calibration of the IDM. And which means that the data, the training data that you're providing should contain different driving behaviors, such that you can have a very good calibrated car following models. And finally, IDM is really powerful. And even though you're using, say, like other coupling model, and you just want to select IDM as a baseline, I think Bayesian IDM is already good enough for you to select it as a baseline. And it's a very simple with a very basic assumptions. Also, it can obtain unbiased motion states, but you have a very good performance. So here are the references of this work. And if you want to learn more about the details of this, welcome to read our preprint, which is already online on archive. And by the way, all of these experiment conducted in this talk are just public with the code on GitHub. So feel free to download the code and run the experiment by yourself. And thank you for your attention. And any questions from the audience?
Thank you so much for your presentation. It was really interesting to know that combining Gaussian process to Bayesian inference could help reduce calibration bias. And also can't wait to look more deeply about how stochastic simulator works. Okay, as he said, now the floor is open to the audience. So please unmute yourself to cast a question, or feel free to leave it on the chat box also, so that we can read it out for you.
Hello.
Hi.
Oh, hi. Thanks a lot for a very nice presentation. I'm curious about one thing. If you are to go through the route of making more personalized IDM predictors for that, because driving styles are different for humans, and every human has a certain driving style. It maybe depends on the traffic scenario as well, or even like the dynamics of the vehicle itself. So if you are to input these types of, or predict for personalized people type of behavior, how would you do that through your model, or does it naturally do this?
Actually, our model is actually a hierarchical model, and as I said before, here is, let's see, yeah, here. In this hierarchical structure, we have a population level parameters here, which can learn the general, or say the general behaviors of most of humans do, right?
Yeah.
And then we set this as a prior for the individual level, which means that the individual level theta D can learn the specific driving behaviors. And this can be, scenario specific. It can be driving style specific. It's just, can fit to the specific driving behaviors that you have for a specific driver. So if you say like you have different scenarios or different styles, you can just directly use a hierarchical model, and you can build it like more complicated. You can combine other mixtures, or say other hierarchical to tell, say, like which is a driving style, which is scenario specific, and everything can be combined into this hierarchical framework. Hope that can answer your question.
Are there any more questions from audience? If not, I have one for you. I first want to know that if the method you use, Bayesian by GP, also has a risk to fall into local optima, which most of the optimization methods have. And if it is, I am curious about the things you did, like such as specifying the prior distribution in order to prevent that.
Yeah, actually, out of the optimization method can fall into the local optima. And the reason we are using the Bayesian method is that we can combine some prior information into our framework, right? So yeah, it may fall into the local minima, but the Bayesian method is actually a more robust way to do the optimization, because when we come to the ground truth of the Bayesian method versus the frequentist method, is that the Bayesian method is actually an advanced version of the frequentist method by assuming like plus another regularization term, because we have the prior information, right? So this can help us to say like, if I want to find a local minima, I want to find it around my prior, right? Because we have a prior information about like what kind of parameters it should be, what the range should be. And so Bayesian methods in general is actually a more robust way to solve this problem.
I see. So like while you were doing research, did you have like any challenges about that, like during your research? Because I'm having it.
Yeah, actually, it's a very interesting question, and I think most of us in the audience may have this question, and also face on different kind of challenges when doing research. So, yeah, sure. I also have this kind of questions. So, at the beginning of this project, I was also doubting that is IDM really work, because as you know, this is a very actually a textbook algorithm that we have already learned in the textbook, and this is very simple. And we seldom do research on a very mature algorithm on which have already been studied for like decades. So I really doubt that it's really powerful to model the car forming behaviors. So I was kind of confused about everything. Then I just keep faith and trying to do experiments, and then I found some very interesting results. From a very little interesting results, then I can go further, and we can review the whole stories behind this mechanism. And by the way, I also inspired a lot by my advisors, and he always inspired me a lot and give me a lot of support. He just said, try to do it again, and we can have some better results here. So yes, I think everybody may have these kind of problems. Just keep going on and trying to do it.
I see.
Hi, Chengyuan. So one last question. This is Hao from Georgia Tech. Yeah, sorry if I missed it. I saw you use the OpenACC data set, and from my own experience, I know those data sets include different scenarios, including speeds, oscillation types, acceleration, decelerations. I'm just curious, have you found difference in your calibration results when it comes to those different scenarios? For example, if you find, is it more difficult or challenging to calibrate in congested area as opposed to free flow cases, or deceleration against to high accelerations? Yeah, if so, do you think they indicate something related to physics? And what could be those insights? Thank you.
Yeah, actually, this is a very good question. So, as I said before, if we want to calibrate a very good car forming model, we need to provide enough information in the data. So this data should include like acceleration, deceleration, free flow speed, and everything. So yes, for the first part of the question, yes, we have observed the different results by using different scenarios. For example, in this trajectory, in this specific data file that I use in this OpenACC data set, we can have some very abrupt acceleration and very abrupt deceleration here, right? So this can lead to a large acceleration term alpha and a very large deceleration term beta. And I think this have some physical meaning. Means that we may need to take some like aggressive decision when facing in these scenarios, right? So as I showed before, here. Yeah, if you can look at this data set, these are just the results from the Heidi data set. And this is a human driving data. And I just mainly calibrated on the stop and go area. And the alpha and the beta are not very large. And if we use the OpenACC data sets, the beta can be a very large, even like 10 or 20. So which means that in some specific scenarios, these parameters really means some physical meaning. And we may calibrate different scenarios by using different parameters. And this also means that even a human driver is actually driving along the road. His driving style, or say his driving behavior, cannot be is also be time varying. So for example, in the highway, in the say like in the specific scenarios in like the Heidi data set, in the stop and go region, the parameters are maybe like this. And in some other region, the parameter should be shifted to another distribution. And I think this is also a problem here. We need to make the parameter to be time varying. So this may be the next time step, maybe the next step of the research direction.
Yeah, that would make a lot of sense. Yeah, thank you for the answer. Great
Yes,
talk.
thank you for your question. This is very good.
All right,